So this video discusses the background for chapter 4 on solving a system of linear equations. And it's important to note that systems of linear equations are ubiquitous in all fields of science and engineering. So let's take a look at for instance, a mechanical engineering example where we here have this construction of bars and we have some geometrical parameters there. So we have the lengths of the bars, the width of the total construction. And we also see that at this point A, we enact a force of 4,000 newtons. And the idea is to compute the forces that are enacted on these connection points. So the forces that each of these bars holds and that is then concentrated in these connection points. And that's obviously an important and relevant problem in mechanical engineering or civil engineering. Now, using basic geometry and a force balance in every node, well, we can write out a force for every bar, and this will result in this system of equations. So based on that force balance, we can write up 8 equations for each of these 8 bars, 1, 2, 3, 4, 5, 6, 7, 8, with 8 forces, so the force within each of these bars. This is a system of linear equations with the same amount of equations as there are unknowns. So we should be able to solve this, or try to solve this at least. That's an example of a linear system in mechanical engineering. Another example is from electrical engineering, where we have this electrical circuit over here. There are a number of voltage sources. We have some electrical resistances here, and the idea is to calculate the currents through each of the loops within our system. And for that, we can use Ohm's law. So we just look at the voltage drop across each of the elements within a circuit, and then we tend to use Kirchhoff's law in order to check that the net voltage drop over a closed loop should be equal to 0. And that's what we then get. This gives us 4 equations, so 4 loops with 4 equations. And in every equation, well, we have in every loop, we have one designated current. So this gives us 4 linear equations in 4 unknown currents. And again, this is a linear system, 4 equations, 4 unknowns, and we can try to solve this. In the previous examples, the linear systems were relatively small. So we had a 8 equation example for the mechanical engineering with the forces in the bars. We had a 4 equation and 4 unknowns example for the electrical problem. But practical linear systems in real engineering problems can get very, very big. For example, let's take a look at this numerical simulation of turbulent flow around the landing gear of a Boeing 777 airliner. When solving this simulation, and that's a computational fluid dynamics simulation, at some point during your numerical method, you have to solve a linear system in order to get the pressure fields, and that gives you a linear system. So the pressure is a solution of this linear system. Now, this system has about 20 times 10 to the power 9 unknowns for this specific case. So this means that in every point in the discretized domain, we have to compute the pressure in that specific point, which leads to a very, very huge amount of points where we need to compute this pressure. And it's all interlinked. All these equations are interlinked, which leads to a dense and very large system, a very large linear system that we need to solve. So these systems can really get very, very big. Also, practical linear systems can get extremely computationally expensive, and actually they are can get so expensive to solve that they are used in the LINPACK benchmark. And the LINPACK benchmark is actually the benchmark that is used to compile the top 500 of most powerful supercomputing systems around the globe. So the performance that these systems attain when solving a dense linear system of the form of AX is equal to B, how many floating point operations that such a system can attain per second, that is a metric for how powerful that computer is. And that's basically how we rank the most powerful supercomputers in the world. So these linear systems can get really computationally expensive, and that's why they're also used as a benchmark for assessing the power of these computers. Now, how would we solve such linear systems by hand? And I'm assuming all, if not most of you, have at least some notions of linear algebra. And the idea is, well, when we are faced with a system of linear equations, the most natural way to solve this is to convert this system of three equations with three unknowns, x1, x2, and x3, into a matrix representation, where we have here our coefficient matrix. We have the vector of unknowns, x1, x2, and x3, and the right-hand side, 6, 9, and 2 in this case, such that if we perform the matrix multiplication of this coefficient matrix with this unknown vector, we recover our original system of linear equations. So this is the matrix representation of our original system. And then what we try to do is, well, we will use row reduction of this matrix system over here. So we use elementary row operations on those on the matrix, which correspond to adding different equations to each other or multiplying both sides of the equations with a constant factor, etc. And this allows us to get this system into a form, in this case, a diagonal form, and that gives us immediately the solution. So in this case, we see that the linear system in matrix representation over here, if we just multiply the matrix with the unknown vector, then this clearly says that x1 is equal to 1, x2 is equal to 3, and x3 is equal to 2. And that's how we actually solve these systems by hand. And that process is known as Gaussian elimination, which is also the basis for one of the methods that we will be seeing later today. Now, let's have a look at some systems which are easily solved. And this all depends on characteristics of the coefficient matrix A. For example, the most simple class of systems, class of linear systems to solve, are diagonal systems. Now, diagonal systems have non-zero entries on the diagonal and zeros everywhere else. And this indicates that, for example, the first row has no contributions of any other unknowns other than the first unknown. So this means that the first equation or the first row in this matrix system is decoupled from all the other equations in the system. Because if we read this from left to right, we see that A11 times x1 is equal to b1. And the same holds for the other rows. For example, row 2, we have that A22 times x2 is equal to b2. So solving these diagonal systems in which the linear equations are decoupled from one another simply comes down to solving many single equations which are not dependent on each other. So in that sense, solving such a big system is as easy as solving a single equation. You have to repeat the process a couple of times. So in that sense, we see here the solution can easily be computed independent of the other solutions in the system. Another example of a system which is easy to solve is a upper triangular system or a triangular system in general. And here we see an upper triangular system, and that means that, well, we have only non-zero entries in the matrix in this triangle, in this upper triangular part of the matrix. And all entries below the main diagonal are equal to 0. Now we can solve these systems using a process known as back substitution. And in back substitution, well, we start from the final row and work our way up. And we see that this final row is the same as the final row in a diagonal system. So this means that this final row or the final equation in this linear system is decoupled from the others. So we can just as easily compute the value for solution x3 by simply dividing the right-hand side b3 with the coefficient a33. Moving up one row, well, we see that the equation here is dependent on x2. So we have a22 times x2 plus a23 times x3 is equal to b2. Well, from the previous step, we already know the value of x3. So the only unknown in this equation is x2. So again, we can recast this into an explicit formulation for the unknown x2 by writing b2 minus a23 times x3 divided by the diagonal coefficient a22. And we can do this because x3 is known. And then again, once we know x2 and x3, we can move up one row. And here we see the first equation is dependent on all three unknown variables, x1, x2, and x3. However, x2 and x3 are known from previous steps, so we can simply make an explicit formulation for the unknown x1 using the known values of x2 and x3. So we can solve this by starting from the last row and working our way back to the first row every time substituting in the values for the unknowns that we compute in the lower rows. And that's why it's called back substitution. Another triangular type of system is a lower triangular system, and again the same reasoning holds. Here we have that the lower triangular part of the matrix is non-zero and everything above the main diagonal is equal to 0. We start in this case from the first row, which again is a decoupled equation, so then we can simply compute x1 as b1 over a11. We can then work our way down and substitute the known value of x1 into this equation for x2 and easily compute x2. And in this way, we just keep going forward towards the last row using the substitution to compute all the values, all the unknown values in our system. Now, what is the numerical approach to solving such linear systems? Well, there are two main classes of methods, and the first class of those is a direct method. And examples of those are Gaussian elimination, Gauss-Jordan elimination, and LU decomposition, each of which will be discussed in a separate video following this one. The strategy here is to convert the system into a form which is easily solved, like the one we saw in the last slide. And then we can simply directly solve this to full precision. So we just solve it in one step that we get the final results. Now, how does this look? Well, we start from a dense linear system here on the left. We work our way towards a system which is more easily solved. For instance, this one, a upper triangular system by using these row reduction operations. And then we can solve this upper triangular system using back substitution. And then in one step, well, we can directly compute x3 from its equation. In one step, we compute x2 from its equation and x1 from its equation. So there are no iterations involved. We directly get the final answer for the solution. In contrast, there are also indirect methods, and examples here are Jacobi, Gauss-Seidel, or Krylov subspace methods. And in this case, well, we try to convert the system into an iterative system, so in a system which is amenable to an iterative scheme. And instead of solving it directly in one step, like we do in back substitution, we iterate and keep on improving on this solution that we have until we reach a certain desired accuracy. For example, we could do this for the same system in the following way. So here we have a dense linear system on the left here, and we can, each of the rows of this matrix corresponds to a linear equation, which we can try to make this explicit for one of the unknowns in every row. So this is just this system, but then written in another way. However, we see that now, well, we cannot really compute x1, x2, or x3 because they're all dependent on each other. So in contrast to this back substitution where we have one independent equation and then we just substitute the value that we compute into the other equations, here there is no such thing. We cannot compute x1 without knowing x2 or x3. Same holds for x2 and x3. However, instead, we can start from a certain initial guess for x1, x2, and x3, and we just plug this initial guess into the right-hand sides of these equations, and we iteratively try to improve on the accuracy by making the solution in the next iteration step equal to this right-hand side evaluated at the previous iteration. So in this sense, we can try to improve on this accuracy by doing iterations in a very similar way that we also solved nonlinear systems iteratively, like we saw in the last video lecture. Now, where lies the focus in this course in 2WN50? Well, we will focus on linear systems of the form AX is B, which have a unique solution. So that means that A is a square matrix with n rows and n columns, which has full rank. So that means that we have no singularities, we have no singular matrix, we do not have any inconsistencies, unless otherwise specified. We hope to find unique solutions to this system. Also, we focus only on direct solvers and omit iterative solvers that were discussed in the last slide. If you'd like to learn more about these kinds of solvers, I highly suggest that you follow the course on numerical linear algebra 2WN40.